Right. Thank you, everyone. Welcome to our dynamics lecture today. So first, I wanted to start with answering a question from one of my students. So the question was, what is the C here, and what is A, what is B? So I am sure when you were studying yourself, so probably you also thought what is A, what is B? So the answer is, you can also check our textbook, but as I said earlier, if something, some parameters, some concepts is not clear from one textbook, we always have alternative textbooks as well, right? So now I will try to show you one specific example from Miriam and Craig's book, although our core textbook is available. Here you can see some extra information from the other textbook that I provide you as an alternative and which is available in the library. So here, clearly you can see that because we are able to represent our motion as a circular motion, here you can see C is actually the amplitude of the displacement, and since it is a circular motion, we can actually resolve it into its components A and B in some cases where it can make us or where it can prove useful, right? So this is the reason, and this is where the C equals A squared plus B squared, right? So this again highlights the importance of checking alternative textbooks and try to understand from different resources. So I hope this clarifies the question. I'm not able to identify the student who asked the question to me, but it was after one of our lectures. So first, I wanted to clarify this subject, this point, before I continue with from where I left in last lecture. So now we can continue with our subject from where we left. So it was damped and forced vibration, which I told you that probably the most complex thing or concept that you can see in our lecture, introductory lecture to vibrations. And we were talking about the main governing equations for applied force and applied displacement. So I'm just covering. I know that we covered them last lecture. And we also mentioned that since it is having a kind of external force, the solution has two different components. One is complementary part, which dies out with time due to the friction within the system, but the steady state portion is permanent on the system, and we were able to identify the complementary part can be represented by those three equations as we saw in subsection 1.3, right? So you are going to check the characteristic equation, and depending on the value of the characteristic equation, you are going to decide in which category the motion, the system belongs, and then you are going to use the respective equations if you are asked to identify the complementary part of the solution or the displacement of the mass. But we also know that there is a permanent part, permanent displacement, permanent equation, or steady state part, which is always present in the system as soon as we apply the external forces or external displacement. And we told that since the forcing function, the outside, the external forcing, external force or displacement is harmonic, then we are expecting the displacement to be also harmonic. I will try to explain this, what I mean by that shortly. And I think last time I told you, and I asked you to remind me in the beginning of the lecture, what is the phase angle again? And in our maybe previous equations, maybe it was positive, and somehow it is like negative here now, negative phi. Phase angle is negative somehow, but why? I will try to explain this as well before we go further into the topic. But before, again, we are assuming the forcing function or displacement is harmonic, therefore we can assume a harmonic solution of sine wave. I will try to explain why we assume that and how it is going to happen this way. So, again, mathematical parts, you are also not very interested about this, but finally, we know that after a couple mathematical manipulations, we got something called x prime. What is x prime here? You have motion, periodic motion we are assuming, and the x prime is the amplitude, the maximum value of this displacement. And there is a phase angle, phi prime, and again, by some mathematical manipulations, we are able to calculate what is this phase angle based on function, as a function of some different parameters as omega 0. What was omega 0? Frequency, is it omega? Is omega frequency? Is it? Come on, guys. Is it frequency? Forcing frequency. Perfect. It is forcing frequency. And what is K? Spring constant, stiffness, whatever. Correct. So, we also know what is C. So, we can calculate what is that phase angle. So, now what is that phase angle? Again, here I added two different graphs from the same textbook of Miriam and Craig's textbook. This is not available in our core textbook. So, if you read a couple different reference textbooks, I think it will help you significantly. Here, first I want you to understand, in this system, we have an externally applied force. So, F0 is the applied force externally. You have a mass, M, and you are applying F0, the force, but this is periodic. F0 sine omega 0. Okay? So, F0 represents the displacement, and we have also X. What is X? X is the displacement. Capital X is the amplitude, the maximum amount of it. Right? So, this graph shows us you are applying a force and displacement follows. How this happens? Again, imagine I am representing a mass. I actually do. And from right hand side, you are applying a force on me. You apply the force, and there is a damping in the system, right? We have dampers here. Do we? Yes. Right? So you pull me, you pull the mass. Would you expect the mass follow the force immediately, or you would apply the force and the mass would lag a bit behind? It will still go there, but
if you're going to use a spring-start coupler, then there's a very good chance it will probably lag.
okay, I cannot hear now, but yeah, probably, yeah, it lags, right? So we apply the force due to the dampers, thank you. So due to the dampers, it will still follow, but it will a bit lag behind. So this is what happens here, okay? So you apply the force, displacement increasing, but coming a bit late due to the damping of the system. So the difference between the applied force and the displacement, how much it lags, is called the phase angle. In this motion, because the displacement follows behind, it lags behind the force, this is why in our previous equations it was shown as, where it is, -0. Okay? So I think this hopefully helps you understand a bit. So these are two examples, with different phase angles anyway, so just trying to show you also as the phase angle between sine waves as well. Because you are applying the force. So what I told, because we assume that the external force is periodic. So this is force. The solid line is, as you can see, it is harmonic, right? Sine wave. So this is why we expect the mass to follow the same displacement or same form. Because you are pulling, right? Mass is coming. Before it comes, you are already moving to the other side, so mass follows. Force goes, mass follows, force goes, mass follows. So this is what happens, and the difference between their motion is the phase angle. That's it, I think. Now we can continue. Again, I don't expect you to derive the equations. I want you to understand and know when you will use which equation. When you see the purple background, you understand that these equations will be available to you. They will be given, but there will be different equations in the formula sheet available to you, so you need to be able to understand which equation to use and when to use. This is quite straightforward, as I explained earlier, so you need to analyze the system, what is given, what kind of system you have, do you have force, do you have displacement, what is applied. So please spend enough time to understand the questions. Then, after manipulations, you are going to have this x prime, which is amplitude of your displacement, and the phase angle. They are all given to you. And we also have magnification factor, which is the ratio of displacement under the forcing frequency, and this is ratio over F0 over K, which is static displacement of the mass. Again, magnification factor. Please make sure that you are able to explain what is magnification factor if someone asks you. And be aware that there are different, the definition is the same, but there are different forms of magnification factor. In forced and damped systems, it may be different. In undamped systems, you may have, again, different graphs for the magnification factor. So make sure that you understand everything about magnification factor. Right, you get those equations anyway. Now, I remember putting this extra slide from another book. The book of Rao, Singresho, I think his name. So Rao, Mechanical Vibrations. This is also available in our library. The reason, maybe before I need to ask you. So magnification factor, right? Question. Is it possible to have negative magnification factor? Or if we have, physically what does it mean? I remember the question, it was a couple years ago to me. Okay, magnification factor, I got it. But can we have magnification factor negative? And what does it mean if you have a negative magnification factor? So this was the question. And I tried to see whether, we have a good definition or explanation for this in our core textbook. And I thought maybe it could be better to have this example. I'm giving details, so in case you would like to have a look. Example 3.1. what you need to do, what you need to see here, x is minus. If x displacement minus, probably you will get minus magnification factor. So what does it mean physically? As you can see, we have a kind of piston here working motor. So due to these vibrations, the bar here, the column, is making a harmonic motion up and down. So physically, what do you think? What does it mean? Magnification factor negative. We are having that x minus. X is the amplitude. Amplitude is minus. The point here, probably you are going to check this, right? Who is going to check? After lecture, immediately, without even having a break? Great. Thank you very much. So this is what is expected, right? In theory. But still, in practice, it would be great, really, if you could do that. I'm just trying to tell you what happens here. Probably, because of this rotating motion, probably, the force appears to be applied upwards. At the same time, actually, the bar moving down. So force and displacement are out of phase. If they would follow each other, we would call it in phase. I will tell you next week a bit more details. But if you are forcing upwards and the mass going down, they are out of phase 180 degrees. Okay? So in this kind of cases, you may have magnification factor negative. I just wanted to highlight, so I thought if this is a question of one of my previous students, probably one of you also could have the same question. Okay, now, this is quite an important graph. As you can see from the graph, this is magnification factor as a function of frequency ratio. We discussed this before. So when the frequency ratio or the forcing frequency and the natural frequency are getting very close or 1, you see that actually the displacement or magnification factor getting so high or trying to push the limits of the system. And what you need to be careful here, so these outer curves representing C over CC 0. What does it mean? There is no damping, no dampers in the system. So if there is no damping in the system, you can see that it is going asymptotically, like, high and high, without any boundary. But with even a relatively small amount of damping, you see with this one, like 0.1, 10% damping you have, and you can see that actually the magnification factor can be limited. It's not going much higher. If you increase this ratio a bit higher, you can see like even like quarter, 25% gives you a quite effective solution. And you see, if you increase a bit further, obviously, then it is getting, the displacement levels getting lower and lower. So, as I said, yeah, this is also a quite important graph. And I will just check what is the next video that we can talk about. Or should I ask here now? Okay, later I will ask the question. Have you heard about James Webb Space Telescope? So they are doing something here and try to see why they are testing this against vibration levels. far away now, right?
This December
this
22nd
one?
may become known as the
Aerospace
day the
guys, maybe.
universe changed. That Wednesday, NASA expects to launch the James Webb Space Telescope, the largest and most expensive instrument ever flown, 100 times more powerful than the 31-year.
So this is not part of James Webb, right? So this is Cheops. So they are testing at different frequencies. Frequency increasing probably. So it is still tested, right? Higher frequency. You may even not really see now, but again, still tested at high frequency. So here comes our discussion session of today. First one at least. We will hopefully have today 2 discussion sessions. So please try to tell you to the person next to you. If you don't know each other, please first introduce. Still maybe you are not you didn't have enough time to do this before. So the question, why we are testing at different frequencies and what is the benefit of it? Why we are doing that? Why they are doing all those very expensive vibration tests on those delicate machines? So please discuss 2 minutes and then we will continue, right? So, yeah. You haven't met before? Am I so boring? So magnification factor. So we have a vibration with a say forcing frequency of F0. F0 is the forcing frequency, force applied, the maximum amount of the force that we apply to the system. So when you have a vibrating system with under this F0 force, your system gives you a maximum amount of displacement, okay? So amplitude we call. Put it aside. But this is, you are forcing the system with that F0. And you have a magnitude aside, okay? This is one. And the second case, you have this F0, you just, in static conditions, you just put this force on the system, it will produce also a displacement, right? So this is second. 1/2 is the magnification factor, which means if you are just applying a force on a system statically, it will provide or produce a displacement, okay? But if you apply it in a periodic harmonic way, it is producing a higher displacement when you apply it in a harmonic way. So the ratio of these two gives you the magnification factor. So the displacement under dynamic conditions divided by displacement under static conditions give you the magnification factor.
Static condition is what?
Sorry?
What is the static condition?
It is not repeating, so it is just static. You apply one time, under static conditions, so it is not dynamic. Dynamic means that you are applying harmonically. Static is that you are applying and trying to pull it.
So what it means that if we apply harmonically, it will dissipate and it will have more displacement.
Correct. So since it is a higher displacement, if you divide it by the static displacement, this is giving you magnification factor, and you understand the same force still, but it is magnified.
Yes.
The displacement magnified, so magnification factor is the magnification amount of the static displacement basically. Make sense?
Yes, thank you very much.
Great. Now, discuss. CC, critical damping factor, right?
That is what you very much.
This is the optimum amount of damping that will give
Yes, I just don't remember what you mean for this.
equation for it.
Yes, CC.
2 omega m. Omega n. 2m omega n. 2 times mass times omega n. Good.
Question, I have my thesis.
Yeah.
They test them at particular frequencies because this is the natural frequency of something that resonates hot, great.
Correct. This is the main reason, yeah.
Yes, and they test them in the first place because these are machines that are so delicate that the dust on them will work. But they're supposed to handle a rocket launch, and we need to test them so we can know if they will handle that rocket launch. If they don't, because if they don't handle that rocket launch, congratulations, we wasted God knows how many millions of dollars on nothing.
Exactly. Correct. Great.
Also, you told me something earlier that there was something I should go check that without something I should go check directly after this lesson. What can I ask what it is?
Just like, again, it is about, I want you to check the textbooks that I provide you. Okay, so I give some details about textbook down there. So also negative magnification factor, I wanted you to understand the reason.
Also, take a look at this. I wrote this one. MF is
Yeah,
negative.
correct.
This? Wait, this is enough.
Yeah. For the purpose of our case, it is enough. But what I want you to do, ideally, go to the book that I provided, Rao's book, and try to check, what the book is talking about. Good. Yeah, it is in a couple slides back. Rao, SS Rao, the book, author name. Great. Thank you guys. Now I think
Out of phase yani.
evet, evet.
Mesela orada o structure'ın sağlamlığı için aynı out of phase olmasını, phase içinde olması bir şey değiştiriyor mu? Out of phase olunca daha çok damage görebilir.
Değişir duruma göre. Duruma göre değişir. Ona iyice bakmak lazım. Yani bazı yerlerde mesela o istenen bir şey olabilir. Out of phase olmaları.
Birbirini cancel ediyor mu?
Uygulamaya göre değişir yani. Yani bazı uygulamada sen bu tarafa doğru uygularken onun o tarafa gitmesini isteyebilirsin yani. Duruma göre değişebilir o. Thank you guys for the discussion. And now we are going to consider very important concepts, very important applications of the 1 degree of freedom vibrating systems. So, seismometers and accelerometers are two typical examples that work based on the principles that you already know. You see? So, we have practical applications. And here, what you see is actually a kind of simplified schematic of a seismometer, for example. Of course, in practical terms, in real-life applications, they look probably much more like sophisticated, but the principle, the working principle is that. So, now I will try to show you that with the information you know so far, actually you are able to analyze those complex seismometers or accelerometers. But the condition, because the same system actually could be used as an accelerometer or seismometer. So it really depends on couple important parameters, and we are going to discuss under which circumstances this device could be used as an accelerometer, and under which conditions it could act as an accelerometer. So we are going to hopefully try to finish this today, and hopefully by the end of this lecture you will be much more confident about the concepts you have learned so far. The main idea, again, for us engineers to be able to simplify the systems and try to get the correct free body diagrams and apply the Newton's second law, FMA. So this is what we try to do here, but in order to analyze the system and create a free body diagram of this system, one thing that we need to be quite careful about is the delta, displacement of the whole system, and Y. Y is the displacement of the mass from the equilibrium position. So now I'm going to imagine now this base is the ground. I hate to give this example now, but imagine an earthquake. When the earthquake strikes, the whole system is getting this delta, the displacement. The whole system getting this. Not just the mass or not just the frame of the equipment. Okay? So we need to differentiate between those things. Delta is the displacement of the whole frame and the system included, or the mass included. Y is the displacement of the mass only. And you can see we have spring and damper in the system. When we apply the Newton's law again into the system and considering that the displacement of the mass under an applied external displacement of delta will be Y plus delta, because Y coming from the ground, and also the mass probably will have an extra displacement. Therefore here, the only complex thing that you need to think about here is the displacement. It should be delta plus Y. And when you apply, this is actually written here, Y plus delta is total inertial motion of the mass. So this is the free body diagram. Anyway, quite simple one. So when you imagine the mass is going upwards, obviously the damper will try to pull it down, Cy, C times velocity, and the spring will push it down. So this is why it is downwards Ky. And you need to be aware that actually we considered upwards Y as positive when you are writing these equations. But equation form is the same anyway, and we are expanding and arranging against some mathematical manipulations. And if we assume that the delta displacement is delta 0 sine omega 0 t, which is again, we are assuming that the displacement coming from ground is harmonic. I have been watching, unfortunately, again, some videos of earthquakes recently, and it is quite, I don't know, obviously there are some reasons for it, but you can really see that actually the motion of the ground is quite a periodic motion in earthquakes. So this is not a kind of unrealistic assumption. So it quite represents almost the real applied forces or displacement from the ground. So since we assume that the external applied displacement is periodic and we can represent it by sine waves, again, as we discussed before, you can also assume that the mass also will be moving as a function of sine waves. Doing these all, again, mathematical manipulations, putting delta as omega 0 sine omega t in the equation, you will see that our main equation is in the form of the last equation here. And I am sure it looks a bit familiar, but there are something different based on our displacement, initial displacement considerations, like as delta plus Y. But here you can see easily, actually it is the same equation you obtained or we obtained earlier for reporting frequency, given F0 is represented by m delta omega. Equations are the same form. You see, 1 degree of freedom system that you may think it is oversimplified or like, why you are teaching those things to us, they are quite simple, like, what we will do in real life, what they represent. This they represent in real life. With simple manipulations, actually, even 1 degree of freedom systems can be used to identify, analyze very complex situations. So I just want to tell you one thing, guys. I am aware of the requirements of a higher degree of freedom systems for analyzing some like complex systems, for example. But one thing that I learned so far, more experienced engineers try to reduce the complexity of the systems further. And young engineers try to complicate things before they solve. I know it from myself. I was using 3D finite element models in my PhD because I was thinking it is like, before they did 2D analysis, I was just despising, 2D doesn't give me enough, accurate results. And I tried to complicate it to 3D. It was good. It worked eventually after 3 years. But the difference between 2D, very simple systems, and my own analysis was maybe like 5% or something. And I think it was at a conference. A very experienced, a very respected, he was from industry, I think he told, young engineers try to complicate things and try to solve the very complex problems, but experience, or the thing is, in real life, what you need, simplify if possible, obviously, like some problems require complex solutions. I don't agree, I don't disagree with that, okay? I agree with that. But simple solutions or simple approaches sometimes really can give you the results that you need and with a reasonable accuracy. So please do not underestimate the power of simple analysis in engineering. So again, this is x prime. What is x prime? Again, you know it from before. X prime is the magnitude of the displacement that you have, or the mass that would have, okay? And this is represented as with this equation. And again, some further simplifications to our equations. We know that actually this omega is k over m. And then if we input this into our previous equation, and by rearranging or something, we got this one. This equation is very powerful. It is the same as this one, but just with some simplifications or substitutions. They represent the same thing. But now you will see how powerful actually these equations are when you want to get a seismometer or accelerometer. We know this omega 0 over omega n is frequency ratio, and MF is magnification factor. If okay, I think I can come to this later again, but omega, if you see omega, they are circular frequencies. Okay, because omega gives us angular velocity. If you see f, it is linear frequency, and we have an equation between those this f and omega. What is it? Omega equals 2 pi f. Is it? So they are related to each other, but when you see omega, if I understand the question correctly, I'm not sure. So omega, when you see omega, you know it is angular velocity anyway. Frequency and velocity different, but still. Omega here is angular frequency. Okay? If I couldn't answer, please come and see me after lecture as well. Good. So, in some textbooks like Merriam and Craig, for example, you will see instead of MF, magnification factor, it will be just M. But again, they are same things. So it shouldn't confuse you. Right. Now, two very powerful graphs. The first one, we saw it, right? I tried to explain it was blue color, the same one. The previous one was from our core textbook, and this is from Miriam's book. They are the same, okay? The zeta represent C over CC, our damping ratio, but again, they represent the same thing. Here we have another graph, a new one, which is x prime over delta 0. What do you understand physically? What is x prime? What is delta 0? X prime is the displacement of the mass only. Delta 0 is the maximum displacement applied to the frame, to the whole system. Okay? This is very important. X prime is the displacement of the mass, the maximum amplitude of the displacement, and delta 0 is the displacement given to the overall system. And there are really some important aspects that you need to observe in this graph. On the right-hand side especially. One important thing is when the frequency ratio is getting high, we are getting independent of the damping ratio of the system, this ratio getting 1. What does it mean? You are applying a displacement delta to the system, and the mass actually displacing the same amount of delta 0, of applied displacement. This will bring us to a very important point. This is our equation that we derived just now, and as you see, this ratio getting closer to 1 for the high frequency levels. As I explained earlier, the overall displacement of the frame, whole system, and the displacement of the mass becomes equal, which means that you can use the system as seismometer. Because you will be able to measure the displacement of the mass, right? All those things, remember, from the graphs, they are writing on the paper, right? So this is the displacement of your mass, but the displacement of the mass is equal to the displacement of the frame, which is the, for example, again, magnitude of the earthquake, right? So this is how the system can be used as a seismometer. And the next one, as I said, this can be also used as an accelerometer. Imagine the whole system we showed earlier is placed on a car, and you want to measure the acceleration of the car. How? I want to show one thing before we continue, other one. As you can see here, for the small frequency ratio, our magnification factor is getting to 1, to unity. Magnification factor gets unity. And here, we know that magnification factor is getting 1 when the frequency ratio is low. Then, if you cross it, you will get, if the frequency ratio is small, you can see x prime is equal to this equation on the right. You also know from mechanics lectures of last year, actually, delta times omega squared is also maximum acceleration of the system, right? So now, you can see that system actually can be used if you have the right conditions. What is the condition? You need to have low frequency ratio. If you can provide this to a system, then it can act as an accelerometer as well. One question. Let's go back for a second. The displacement meter or seismometer you can use. So the condition was, in order to use the system that we discussed as a displacement meter or seismometer, we had a condition which was the frequency ratio should be high. The question, again, how you achieve this? Can you change omega 0, forcing frequency? You are trying to measure the magnitude of the earthquake, for example. Can you change omega 0? Omega 0, what was it? Forcing frequency. Can you change it? If you do, please let me know. It's quite an important thing. Omega n, can you play with omega n? So you are able to play with this. So you can change K or M, K and M. The stiffness, the spring can be changed, or the mass can be changed as well. So I want to give some time for our discussion, so I'm going to tell you, normally those accelerometers, please check in YouTube, on YouTube, you will see that those accelerometers have a large mass and kind of a weak spring. So please think, what it brings to you? Large mass and soft spring. So the seismometers have this, and try to explain this based on the graph that we discussed. So I'm going to solve this in our next lecture, but we have a video that I want to show you, and maybe we can even discuss shortly about this. So I want you to see and try to understand what is happening.
I'm not going to let that spoil the party.
So he is putting a mass, M. What will happen? Don't try at home. And try to understand what is happening. To be around, I think. Now they cannot stop it, out of control. Thank you very much for joining today, and next lecture we will solve a problem about this. Thank you. Sorry?
Why doesn't this just happen with fluids? Is it because there's not enough mass in it?
It is. Again, just a second, sorry. Hello, hi. Just a second. First, I need to clean the space, clear the space. Come this way.